So as we've seen, an analysis of the energy carried by electromagnetic waves in thermal equilibrium at temperature T classically gives us this result. All right, we have a 2 for the polarization. 4 pi d lambda divided by lambda to the 4th gives us the state density. That's the number of states associated with electromagnetic waves with wavelength between lambda and lambda plus d lambda per unit volume. Okay? And so that makes this the energy that each of the states gets. And again, we get this classically, just this idea that each way of using energy gets k volts T of energy in thermal equilibrium. Really, it's a half k Boltzmann T, but we've got electric and magnetic fields anyway. So classically, it should be k Boltzmann T. This gives us the Rayleigh-Jeans law. We said that this was a problem because the answer to the question, how much energy do electromagnetic waves deserve in thermal equilibrium at temperature T, is obtained by integrating this expression over all wavelengths from 0 to infinity. Now, while this expression is perfectly integrable around lambda equals infinity, that integral will diverge around lambda equals 0. So this gives us a small wavelength catastrophe, which we called the ultraviolet catastrophe for that reason. Classically, it seems that the answer to the question, how much energy do the electromagnetic waves want in thermal equilibrium at temperature T, is all of it. Okay? From this analysis, it is impossible to satisfy the electromagnetic waves. They would just continue to take more and more and more energy until the matter is frozen out at 0 Kelvin. All right. Now, as we said, this is not a problem with the theory. This is not an inconsistency with the theory. The theory is perfectly consistent in this result. How much energy does the electromagnetic wave want? All of it. Perfectly consistent. What's inconsistent is that this is not what we see in experiment. This isn't what our experience indicates. We do see matter come into thermal equilibrium, all right, at temperatures other than 0 Kelvin. So in order to find our way out of this discrepancy between theory and experiment, what we need to do is we need to look to experiment and say, well, what is it that we do see? When we do that, when we prepare a black body, which is a term that's just used to indicate like a piece of metal, something where it just is able to emit all of the electromagnetic radiation that it comes into thermal equilibrium with at various temperatures. What we find is this. There's the 1 over lambda to the 4th behavior associated with the Rayleigh-Jeans law. And what we find is that experimental data follows this Rayleigh-Jeans law quite closely until we get to small enough wavelengths where it dramatically deviates from the Rayleigh-Jeans law. Okay? Goes down quite steeply to 0 for small wavelengths. All right? So clearly, the physical world does not satisfy this expectation for all wavelengths. This is effectively a large wavelength result. So, in order to have a theoretical understanding of the reason for this behavior, we need to have some sort of a functional form for this. Planck was able to come up with this form in the late 1890s. Okay? Now, I think it's quite surprising looking from now that he was able to do this. All right? And they were some of the worst times in his life. He was ready to throw out everything that he had learned about physics. He didn't think any of it made any sense anymore. And he was just throwing things at the wall to see what would work. And what he came up with, very strange, was this. I'm going to write it exactly the same way. All right? These two pieces can be left unchanged. But this middle piece has a striking difference in character from the classical result. All right? So let's first see what happens when lambda grows without bound. If lambda was very, very, very large, so that beta hc divided by lambda was very small, let's see what happens. Well, if this is small, of course, I'm thinking expansion. So I would say e to the beta hc divided by lambda is approximately 1 plus beta hc divided by lambda plus 1 over 2 factorial beta hc divided by lambda all squared, plus dot, 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 and then of course minus 1. The 1's cancel out. And now I can take a factor of beta hc divided by lambda out of the denominator. And as lambda tends to infinity, this effectively becomes 1 over beta. Which is K Boltzmann T. All right? And that's exactly what it is in the Rayleigh-Jeans law. So this has the correct behavior as lambda tends to infinity. That is experimentally verified. As lambda tends to 0, on the other hand, now beta hc divided by lambda tends to infinity. All right? So that means e to the beta hc over lambda tends to infinity even worse. And so that means that this would tend to 0. And so that gives us this characteristic sharp turnaround in the Planck distribution. All right? Now, I've introduced all these symbols, H and C. What do they represent? The C is the speed of light in a vacuum. Okay? Standard symbol for that. C is the speed of light. Okay? This H was an unknown constant to be fit to experiment. All right, and Planck, I don't know specifically what he got, but today, it's about 6.626 times 10 to the minus 34. And I'll write it out. Or sorry, joule seconds. All right. 6.62607,004 times 10 to the minus 34 joule seconds. Now made exact, if I'm not mistaken, by the definition of the kilogram. Okay? And again, this at the time was fit to experiment to this black body radiation spectrum. All right? So this allows us finally to answer the question, how much energy do electromagnetic waves in thermal equilibrium at temperature T get? And we'll answer that question by adding up all this energy density over all wavelengths. All right, finding the area under the red curve. Now, This form of the Planck distribution in terms of wavelengths is preferred by experimentalists. Theorists are more comfortable working with frequency, at least most of the time. All right? So how are we going to turn this into frequency? Well, wavelength times frequency is equal to the speed of light. So wavelength is equal to the speed of light divided by the frequency nu. So I'm using the symbol nu for frequency here. All right, so let's see what this would turn into. Hc over lambda becomes h nu. This exponential becomes beta h nu. And now I'm going to turn this into an expression involving a frequency window d nu. So if we take the differential here, we find that d lambda is equal to minus c divided by nu squared d nu. This negative sign is really just telling us that if the wavelength gets bigger, the frequency gets smaller. It's not appropriate for us to include that negative sign when looking at energy density in a window. Okay? I'm just looking at a certain window size. I'm not interested in the fact that when lambda increases, nu decreases. So for that reason, I'm just going to unapologetically ignore this minus sign. It's like I'm just looking at the absolute value of the window size. Sometimes that throws people off. So that's why I wanted to mention that. All right, so I would have d lambda over lambda to the fourth. Let's see what happens to it. All right, d lambda was c over nu squared d nu. And then I've got c over nu to the fourth. So rearranging this, you'll find that it's really just that 4 pi nu squared d nu divided by c cubed. All right? Now, as I said, we can find out how much energy the electromagnetic waves deserve in thermal equilibrium at temperature T by doing this integral. But before we do that, let's take a minute to talk about what this expression indicates about the nature of electromagnetic waves. All right? As we've seen, this expression is fine when the wavelength is large, when the frequency is small. It's not the large wavelength, small frequency behavior that is the problem leading the ultraviolet. Catastrophe. It's the small wavelength, large frequency behavior. So let's see what happens when the frequency is large. Well, if the frequency is large, then e to the beta h frequency is really, really, really large. And so that indicates to us that maybe it's a good idea for us to divide the numerator and the denominator by e to the beta h nu. So I can say all right? All right. In the unexplored region of large frequency, this is 1 over 1 minus small. So I can expand it. And what we see when we expand this is something somewhat surprising. We get an infinite sum of Boltzmann factors. This one is associated with a state of energy h nu. This one is associated with a state of energy 2h nu. This one, 3h nu, and so on and so forth. So, from this perspective, the reason that this solves the ultraviolet catastrophe is that, unlike classically, there is a minimum amount of energy necessary to excite electromagnetic waves with frequency nu. You need at least h nu worth of energy to excite those modes. If that energy is not freely available, then those modes will not be occupied at the expected rate in thermal equilibrium at temperature T. Notice, of course, that as always, here this beta h nu is a ratio of two energies. It's asking what fraction of this ambient energy, K Boltzmann T, h nu represents. If h nu is a lot bigger than K Boltzmann T, then it is unlikely that an electromagnetic wave with that frequency nu will be excited in thermal equilibrium at temperature T. If, on the other hand, H nu is much smaller than K Boltzmann T, then we expect easy occupation. We expect those electromagnetic wave fluctuations to get all the energy that classically we would expect them to have. All right, and this is exactly what happens. The large frequencies are limited by this minimum requirement, H nu. All right? That's one result that really just leads directly on the surface to the resolution of the ultraviolet catastrophe. In fact, even just this one factor would solve the problem completely. That's not what we see. Once we get enough energy to have this H nu, we say, oh, there's another state. 2H nu. There's another state. 3H nu. We get an infinite series of energy states associated with discrete multiples of energy H nu. This was really surprising at the time, okay? Because it indicates that electromagnetic waves have energies that are quantized. They can only occur in integer multiples of H nu. Okay? And this, I think, was what Planck was referring to when he said he was ready to throw out everything that he had understood about physics. Because my understanding is this expression didn't just come to him in a dream. Okay? He worked through this, trying to find a way to limit the occupation of these high frequency electromagnetic waves. All right, he didn't believe it when he wrote it down, but then when he compared it to experiment, it worked. It did fit the data coming out of the black bodies. Well, then, of course, the question becomes, I mean, this is energy contained in electromagnetic oscillations in electromagnetic fields, electromagnetic waves. There's no atoms. What on earth is occupying these states? The answer, of course, we now is the photons. They are the electromagnetic waves themselves that can only exist in these quanta. Planck wasn't ready to really go with that. Einstein was. And he used this to explain the photoelectric effect in like 1902. All right? Was it 05? That special activity.
It's a miracle you did 4.
Those papers. All right. I think maybe he started working on it.
He must have started earlier, but yeah, like the 4 ground papers.
1905. All right. All 4 of them, 1905. All right. So, and then 10 years later for general, anyway. All right. So these represent 1 photon, 2 photons, 3 photons, and you can't really have electromagnetic waves of energy or of frequency nu be excited in a non-integral multiple of H nu. Okay? Now, we only looked at this for large nu. When nu is small, this explanation doesn't make as much sense when h nu is small in comparison to K Boltzmann T. All right? When there's plenty of energy around, it's difficult to make this argument associated with the photons for small frequency. But when I say small frequency, I just mean that this is large. Or sorry, when I say small frequency, I just mean that this is small. H nu divided by K Boltzmann T is small. So I'm comparing H nu to K Boltzmann T. So if I look at a colder and colder and colder temperature, light with lower and lower and lower frequencies satisfies this argument. All right, so we still have this concept of photons for all frequencies. Okay? All right. So now let's find out how much energy the electromagnetic field wants is owed in thermal equilibrium at temperature T. So I'm going to integrate over frequency from 0 to infinity. I'll have 2 h nu over e to the beta h nu minus 1 and then my state density. I'm, of course, going to make a U substitution. U equals beta H nu. So du would be beta H d nu. This is effectively just a scaling substitution. All right? So I'm going to take all my constants out front. So I would get 8 pi over c cubed. Integral from 0 to infinity again. H nu is u divided by beta. E to the beta h nu is just e to the u. And then I'll have nu squared d nu. That's just u squared du divided by beta h cubed. So this gives us eight pi divided by beta hc cubed 1 over beta. And then the remaining integral is u cubed du divided by e to the u minus 1. Now, if you think back, we've seen this integral already. We've seen a general integral of this form. The integral from 0 to infinity u to the n minus 1 divided by e to the u minus 1 du was equal to gamma n zeta n. It came up in our integral representation of the zeta function. So that means that here we're going to have 8 pi over beta hc cubed Boltzmann T, and then it's going to be gamma of 4, zeta of 4. Gamma of 4, zeta of 4. The 6 cancels away. And so what we end up with, when we clean it all up, is 8 pi to the 5th, k Boltzmann to the 4th, divided by h cubed c cubed of 15, h cubed c cubed times t to the 4th. All right, 8 pi to the 5th, k Boltzmann to the 4th, t to the 4th, divided by 15, h cubed c cubed. Boy, that's a strange expression. Look at all those powers. Let's see, at least if it's dimensionally correct first. All right? So, to check its dimensions, I'm going to use this form. All right? This is dimensionless, so I'm not worried about that. The 8 pi is dimensionless, I'm not worried about that. This is an energy. K Boltzmann T is an energy. So let's see what the rest of it gives. What is beta HC? Well, this is HC divided by K Boltzmann T. Planck's constant, H, was energy times time. The speed of light, c, is length divided by time. K Boltzmann T, we've already said, was an energy. So beta HC is a length. So let's see what we got here. Energy divided by length cubed. Yep, that's what we want. Energy density. Remember, this was not the total energy. It was the energy density. Energy per unit volume. All right, so our result indicates that the energy density in electromagnetic waves increases with t to the 4th power, proportional to t to the 4th power. Remember, the energy density in matter at constant density increases only with the first power of temperature. So what we can expect is that when the temperature is small, most of the energy contained in a given volume of space is carried by matter particles. Low temperature is matter dominated. But as the temperature increases, this fourth power increase in the energy density carried in the electromagnetic waves will eventually overtake the matter. And we'll get to a place where the region of space is radiation dominated, such as what happens in the core of a star. All right? Now, before we do some numerical computations with this, let's do a sort of fun computation to see, rather than the total energy, let's see if we can count photons. How many photons do we expect in thermal equilibrium at temperature T? Now, once again, sort of weird to think about the low frequency oscillations in terms of their quanta. They don't really behave that way. All right? They're like particles and waves. The higher frequency electromagnetic waves behave more like particles in some sense. The lower frequency ones can be thought of in some sense more like waves. So what we're about to do is not completely quantitative, but it is neat. All right? So all we have to do to modify our computation to count photons is we'll say, well, wait a minute, each photon carries energy h nu. So if this is the total energy density, right? All I have to do is divide this by h nu, and I'll get the number of photons. So I'll have 2 just like that. I'll do exactly the same computations. All the same stuff will happen. In fact, let me just add that. All right? And then it would be the integral 0 to infinity u squared du divided by e to the u minus 1. Same thing, it's just instead of 4, we'll have 3. All right? So this results in all right, 8 pi divided by beta hc cubed times 2 zeta of 3. 16 pi divided by hc cubed let's put our zeta of 3 here, and then it'll be K cubed temperature cubed. All right, so the energy density goes up like the 4th power of the temperature. The number of photons only increases as the 3rd power of the temperature. All right, and that makes sense, because as the temperature increases, you're exciting photons with more and more and more energy. All right? So those are some of the mechanics of the Planck distribution.